Ask ChatGPT what the capital of France is. It'll say Paris. Ask it again 5 seconds later. It doesn't remember it just told you. It recomputes the answer completely from scratch, billions of operations, just to get to the same word it already said. Every fact every time. The capital of France, the syntax of Python, the atomic number of carbon. Your AI doesn't store any of it. It rebuilds all of it from raw math on every single request. In January 2026, DeepSeek published a paper with a surprisingly simple fix. A hash table bolted onto the transformer. Constant time memory lookup. Zero compute cost. They call it Engram, spelled E-N-G-R-A-M. And it might be the most important architecture change to the language model since Mixture of Experts. Let's break down exactly how it works. Here's the core problem. When a transformer processes your question, every single token looks at every other token. That's what attention is. If your input is 1,000 tokens long, that's 1,000,000 pairwise comparisons. 10,000 tokens? 100 million. It scales as order and squared. And here's the thing. Most of that computation isn't doing anything creative. When you ask about France, the model doesn't need to reason about Paris. It already learned that association during training. But it has no way to just look it up. It has to reconstruct the answer through the full attention machinery every time. It's like if every time someone asked your name, you had to replay your entire life history to figure out the answer. You wouldn't do that. You'd just remember it. The AI industry already has one trick for making models more efficient. It's called Mixture of Experts. Instead of one giant neural network processing every token, you split it into dozens of smaller expert subnetworks. A router looks at each token and sends it to only the top 6 or 8 experts. The rest stay off. This is how DeepSeek V4 works. 27 billion total parameters, but only about 4 billion active on any given token. You get a big model's knowledge with a small model's compute cost. That's conditional computation. Use the capacity you need, skip what you don't. But Mixture of Experts only optimizes computation. The experts still have to calculate everything from scratch. They're fast, but they're not remembering anything. What if some of that capacity could be used for actual memory instead? This is the key insight. Not all knowledge is the same. Some things are static facts. Paris is the capital of France. Python uses indentation for blocks. Water boils at 212 degrees Fahrenheit. These don't change. They don't depend on context. They're just things the model memorized during training. But other knowledge requires reasoning. Debugging code, writing an argument, solving a math problem. These need the model to actually think, to chain steps together to do computation. And right now, transformers treat both kinds of knowledge exactly the same way. They throw the full attention machinery at everything, whether it needs reasoning or just a lookup. DeepSeek's idea is simple. Separate them. Let the transformer focus on reasoning, and give static knowledge its own dedicated, cheap retrieval system. Here's how the Engram module actually works. It starts with your input tokens. But instead of looking at tokens one at a time, it groups them into pairs and triplets, bigrams and trigrams. So if the input is capital of France, it would create pairs like capital of and of France, plus the triplet capital of France. Now here's the clever part. Each of those token sequences gets hashed, not once but 8 times through 8 different hash functions. Think of it like having 8 different filing systems, each organizing the same information in a different way. You look up the same sequence in all 8 and combine what you find. The embedding table itself is just a giant array of vectors, over 2 million slots for the 27 billion parameter version. Each slot stores a learned embedding, a compressed representation of some piece of knowledge. And the lookup is constant time. No attention, no matrix multiplication. Just compute the hash, go to that slot, grab the vector, done. But you can't just dump memory into the model blindly. Sometimes the retrieved fact is exactly what's needed. Other times it's irrelevant or even harmful. So the Engram module has a gate, a learned switch that decides how much of the memory to actually use. Here's how it works. The model takes what it's currently thinking, the hidden state, and compares it against the retrieved memory. If they're aligned, if the memory is relevant to what the model is working on right now, the gate opens. If they're misaligned, the gate stays mostly shut. It's context-aware suppression. The model learns when to remember and when to think, and the whole module plugs into the transformer at layer 2. Early in the network, right where the model is still assembling basic representations. The Engram memory gives it a head start. In fact, DeepSeek showed that layer 5 in an Engram model produces representations equivalent to layer 12 in a standard model. The memory effectively compresses 7 layers of work into 0 compute. So if memory is this good, why not replace all the experts with memory? Because you still need experts for reasoning. The question is, what's the right split? DeepSeek ran experiments across different ratios and found something beautiful, a U-shaped curve. Too much computation, not enough memory? Bad. Too much memory, not enough computation? Also bad. The sweet spot sits right around 75 to 80% experts, 20 to 25% memory. They call it the Sparsity Allocation Law, and when you hit that sweet spot, the results are across the board, plus 3 to 5 points on knowledge benchmarks, plus 3 on code generation, plus 12 points on long context retrieval, jumping from 84 to 97. All with the same total parameter count and the same compute budget. You're not making the model bigger. You're making it smarter about what it stores versus what it calculates. Here's where it gets really clever from an engineering perspective. Those embedding tables, they're just big arrays of vectors with deterministic addresses. The model always knows exactly which slot it needs before it needs it. That means you can store them in system memory, regular RAM instead of expensive GPU memory. DeepSeek tested this with 100 billion parameters of embeddings offloaded to RAM. The throughput hit under 3%. The model barely slows down because the hash addresses are known in advance, so the system can prefetch the embeddings while the previous transformer layer is still computing. The memory transfer and the computation happen at the same time. Think about what this enables. You could have a model with 1 trillion total parameters, where most of them are just stored knowledge sitting in cheap RAM, and only the reasoning parts live on the GPU massive capacity. Modest hardware? So why does this matter right now? Because DeepSeek didn't publish this paper as an academic exercise. The Engram paper is authored by DeepSeek's core team, including their founder, and in early March 2026, something called V4 Lite briefly appeared on DeepSeek's platform before being pulled. Now, nothing is confirmed. DeepSeek hasn't officially said what's going into V4, but the community expects Engram to be a core piece, combining conditional memory with mixture of experts and their other recent innovations. If that's the case, we're looking at a model that doesn't just compute. It remembers. The bigger idea here goes beyond DeepSeek. For years, every improvement in AI meant more compute, more GPU chips, more power, more money. Engram breaks that pattern. It says some knowledge doesn't need computation at all. Just store it. Just look it up. Separating what a model knows from how a model thinks. That's the real breakthrough. And it's an open paper, open code, Apache 2.0 license. Anyone can build on it. The next generation of AI won't just be faster at calculating, it'll actually know things.